Hello, everyone. Welcome
everyone.
to the SETI Cypher Challenge 2016,
Yeah.
the last day. This is Dr. Sam Connolly. I'm almost Dr. Juan Hernandez. And we have here Dr. Jim Madsen from the IceCube Neutrino Observatory at the South Pole.
Yeah. So we just wanted to ask you a few questions about the detector and the science. But first of all, could you just tell us how you're involved with IceCube and what you do?
Yeah, so I'm a scientist, but right now my main responsibility is I'm the associate director of the IceCube project and responsible for the education and outreach efforts.
Okay. So, well, I guess the main question, the most important question is what is IceCube, this detector that we've been hearing about a lot this week, and how does it work?
Yeah. So, you know, the way we do astronomy and astrophysics is we have to have something that we can measure that the object we want to study gives off, right? So the first people who did astronomy just used their eyes, right? And then in the last, century, basically we developed methods to see things that we couldn't see directly with our eyes, but mostly that was in different forms of light. So from physics perspectives, all the way from radio waves all the way up to very high energy light, gamma rays, are all kind of a form of light, right?
Yeah.
And so the idea now is to do the same type of exploration, but using these particles called neutrinos. And they have some advantages, but like a lot of life, things that are advantages sometimes also can cause trouble. So
yeah.
The advantage they have is they can go right through things. They're the only particle we know that can be produced from a dense environment and travel out unhindered. But because they can do that, it also makes them very hard to detect. So you have to build a giant detector in order to see enough of these. So basically what we did was transform the ice at the South Pole into this very strange type of telescope that's able to indirectly track neutrinos.
Incredible.
Okay.
Yeah. So what kind of objects? We have this fantastic observatory at the South Pole, but what kind of objects do actually produce these elusive neutrinos?
Yeah. So there were other neutrino detectors that were built before IceCube, but what makes IceCube unique is the size. So we look for very high energy neutrinos, and so we're looking for the biggest explosions in space, right? And so the most powerful cosmic engines. So even like with supernova, they produce tremendous bursts of neutrinos, but for us, relatively low energy. So we can detect those, but only as like a counter, not tell which direction they came from. Okay, but there are other things like AGNs, for example, that have the potential to accelerate particles to very high energy and produce tremendous pulses of particles as well. And so that's a candidate site. But the real mystery is, where are these extremely high energy neutrinos being produced, and what is the mechanism by which they get to those high energies? That's what motivates a lot of the research we do.
Okay, well, that's interesting you mentioned AGN, because that's what I study. So for anyone who doesn't know, that's supermassive black holes at the centers of galaxies, which have a lot of gas falling towards them. So it's called accretion, when stuff falls onto a black hole and it produces a huge amount of energy. So I study that, but I mainly look at X-rays. As we just heard, kind of traditional astronomy looks at light, and X-rays are light, but just high energy light. Juan looks a lot of optical light, so the light we see. But that's interesting that you can look at them in neutrinos as well. So you kind of told us about the kind of things that we can detect, but what is the actual kind of science, I guess, the big questions that you're trying to solve by detecting these neutrinos from these different...
Yeah, so what we've known since the early 1960s is that there phenomenally high energy particles called cosmic rays coming from outer space. And so just like there's only a few people who are super rich, and then there's more and more people as your salary level goes down, there are fewer and fewer particles the higher the energy the particle has. And so these particles are so rare, basically, if you made a detector that was 10 kilometers on a side, you see about one per year, right? So we've seen, with these different instruments, a few dozen particles of this energy, but that's not enough to tell where they're coming from.
Yeah.
And we haven't been able to figure out what those mechanisms are that literally make these reach energies of 1 million or 10 million times what we can produce, like at the Large Hadron Collider.
Yeah.
So we would need, basically an accelerator the size of the solar system.
Okay, that's amazing
technology, right? So it's not something we're going to do with the technology that we had, right? So the question is, how are they doing that, and where are they coming from? And the neutrinos have this advantage that they're neutral, and they also can go through intervening matter, whereas the cosmic rays are charged particles, and except for the very, very highest ones, energy ones, they get their paths altered as they travel with the magnetic fields. So magnetic fields will change the path of a charged particle. So where you see them coming from going into your detector does not point back to where they were created. And that's the big challenge, right? So one of the primary motivations for IceCube was to see if we can identify what we call a point source, a source that's producing enough neutrinos that we can say they're all coming from the same location. Mm-hmm. We get enough that we can better understand what's the mechanism. And then what's really neat, I think, about how science is done now is it's really what we call multi-messenger astronomy. So almost nothing is going to be figured out by one instrument, right? So you look with your X-rays and you say, yeah, there's a black hole there, right? Or an AGN, or they look with radio telescopes and so forth, or gravity waves. We actually look for neutrinos, and published a paper jointly with the LIGO collaboration based on there to say, we didn't expect to see some neutrinos because that was so far and relatively small, but here's how many here's what we could have seen, right? And we can see.
My computer died on me.
That's okay.
No worries. Thanks for coming back.
So we're back. Okay, so I guess the last question we really have before we go to the floor, as it were, the students' questions is: have you been to the South Pole to the detector?
Yeah. So I've been to Antarctica 4 times. Wow. Three times to the South Pole, and 1 time just to work on another project that's on the coast of Antarctica.
Okay, and what's that like? Is it? I mean, presumably it's very beautiful when the weather's nice.
Yeah, so we go during the summer, and on the coast of Antarctica, actually it gets above freezing during the summer. Typical temperatures still at the South Pole are like it's about 15 below in the summer.
Okay.
Sorry about that. And so, and then kind of the station opens at the South Pole when the temperature gets warmer than 45 below Fahrenheit. So that's about the end of October, beginning of November, and then closes about mid-February. So then the last plane leaves, then there's about 45 people who we say winter over.
Okay.
Wow.
And so we have 2 people. They are typically not necessarily PhD scientists, but have technical expertise.
Okay, yeah.
And they're there to keep the experiment running. We have some occasional issues like with power supplies that fail, or other aspects like that where they physically have to be present to do things. Otherwise, all the data is sent, north via satellite. So most of the time when people go to the South Pole for the IceCube project, they're doing like literally physical work. People think you're like a scientist there doing experiments, but mostly, replacing a computer or, digging snow out of something.
Yeah, really. Yeah.
Whatever it takes to get the experiment running.
Practical science. Yeah. Yeah, brilliant. Okay, so I think we can move on to the questions from the students now.
Yeah.
So I guess this is probably a good one.
Yeah. So from James Gillespie
from Team Internet Explorer. So the question is, how do you determine which direction neutrinos come from? So you said that in some cases, at least, you can work that out, right? How do you do that?
Yeah. So there are two types of events that we see. One type, it turns out there are three different types of neutrinos that exist. So there's an electron neutrino, and there's a muon neutrino, and a tau neutrino. And the reason why we know there are three types is when they interact, an electron neutrino will produce an electron, right? And then a tau neutrino produces a tau particle, and a muon neutrino produces a muon. And so the electrons are highly interactive. So they travel a very short distance, and then basically they create a shower of secondary particles, a burst of light that goes out in a sphere. Okay, and so as you can imagine, there's not much directionality. So for those types of events, we can only tell the direction to within about 10 or 15 degrees.
Okay.
Okay. But the muons can actually go basically the whole time that they exist. They just travel in a straight line, and they can go right through matter as well. So the high energy ones can go many, many kilometers, and so they produce more like a cylinder of light going through the detector.
Right. Okay.
And so those we can get, a degree or less kind of precision on their direction. Not outstanding for astronomers, right, who are used to,
better than 10.
For me, it's arc second precision.
It's not so good with X-rays.
Yeah, exactly.
But,
But,
X-rays
and that's one of the reasons why we need to rely on other types of telescopes to help us pinpoint where these are coming from.
Yeah, so that's usually, Juan says obviously in optical astronomy you can pinpoint them quite easily, but with things like X-ray and particularly even higher energy light, even like gamma rays, it's the same. You can only tell to a certain precision where it is in the sky, and then you have to use a different telescope for the same reason, because they go straight through your detector, so it's hard to tell. Very interesting. Okay, so questions. So yeah. So the next question. So it's about aliens, actually. So the aliens who have been sending the signals have been using neutrinos, as I said. In order to be a living life form, they must follow the rules of Mrs. Gren, which is, I think that's reproduction, movement, growing, things like that. Do you think other aliens would have their own laws of science, and how would that be possible? So I guess, do you think other life forms would be similar to us, or could they be very different?
Yeah, so not really my field of expertise, and I think that's one of the things we always have to be careful of, right? Is even with things that we know about, we tend to get blinded or too narrow a vision, because we say, oh, because this is the way we see things behave, right? Or these are the things we know, then that's the only thing we should look for, right? And so it certainly guides, so we say, oh, if we try to look for inhabited planets, we say there must be water, so we look for signatures of that. There has to be this, this type of environment, because that's the way we know here. And that's a good way as any, because we have to guide these searches, right? But one of the quotes I always like is that, nature is much more clever than human, right? Yeah. And so the amazing thing is, even on Earth, right, you can go back and find environments where the thought was it must be sterile, it's too extreme, nothing could live in there. But then they find out in these like highly acidic environments, or in these really no oxygen, or something, that life has figured out a way to what it needs in different ways. So yeah, there'll be something much more interesting than we can imagine, I would say.
Absolutely. I guess something I personally wanted to ask, whilst we're still on the aliens. So as we said, the aliens are communicating by sending neutrinos. So do we? How easy is it for us to actually produce neutrinos with sort of machines? Is that something we can do very easily, or?
Yeah. So the answer is kind of yes and no, right? So basically, the way we make a neutrino beam, and we have experiments on Earth that do that, is we accelerate protons, and then you just literally can smash them into anything. Right? They just have to knock into something, and that physics is pretty well understood. The proton, when the high energy collision, will create a particle called a pion. The pion decays, and one of the outcomes is a neutrino. And so that produces a neutrino beam. And so, at CERN, for example, they produce, and they have detectors in Italy, and that was the whole, thing a few years ago, where are they going faster than the speed of light? Right? But and then they do that also in the Chicago area, right? At Fermi Lab, and shoot them and detect them up in North Minnesota. But then the other way we produce neutrinos is just at nuclear reactors. And those reactions that take place, neutrinos come out, and they know what type of neutrinos are being produced, and then they measure what type are being detected. And so one of the big areas of studies is this understanding the properties of the neutrinos themselves. They have this property they call oscillations. One type, an electron or a muon or a tau neutrino, but then as they travel, there's a finite probability that they will appear as another type, right? And they're the only particles that we know of that do that, right? So there are multiple measurements, and that's a huge area of study in particle physics, trying to understand those properties. And we actually can do that same thing, because when the cosmic rays hit the Earth's atmosphere, they produce mostly muon neutrinos. And when we measure how many muon neutrinos we see at the South Pole, there's a deficit.
Oh, interesting.
The deficit depends on which angle the neutrinos have come from. And so from that we can, and what energy they had. And from that we can then back out what the properties of the neutrinos are themselves.
Great.
Okay, so let's have a look. Okay, so our next question. Do you want to?
Yeah, so this comes from Sadie Jones, and she said, how did you end up becoming a scientist? Was there a particular moment or event in your life that made you want to do science as a job?
Yeah, my path was not so predetermined. I know I have a colleague, for example, at the institution I teach at, who in third grade said, I want to be a professor, and he knew from that moment he wanted to be a physics professor. So I came from a kind of a large, very low income family. Neither of my parents went to college, right?
Mm-hmm.
And but I had, you know, a lot of curiosity. I had was good in school, right? But even when I got done with my undergraduate, I wasn't sure what I wanted to do.
Yeah.
And so, but I was working for some professors in the physics department, helping edit and produce a textbook. And they encouraged me to go to graduate school, and then to kind of fall into some really neat projects. So my background isn't in astrophysics, not in particle physics at all, but the guy who's head of the IceCube project, I met informally when I was an undergraduate at UW-Madison.
Okay.
Said, well, you know, back in 1998,
Yeah.
you know, apply for a sabbatical and come work with me, you know, because he remembered me from when I was an undergraduate. So you know, you never know what connection is going to be significant, right? And where things are going to go. So now it's brought me all over the world, and you know, the great fortune to be involved with this, you know, incredible project.
Yeah, absolutely.
Thank
Okay, so we've got a few more questions. Okay, yeah, so from Peter Borman, how many confirmed neutrino detections has IceCube detected since starting operation? So I guess, well, it'd be good to know when it started operation for a start, but how many neutrinos?
You know, IceCube started construction in 2002, 2003. As I mentioned, you can only work about 3 months, right?
Mm-hmm.
So it took us 7 seasons at the South Pole to build it. So it's been fully operational since about 2011, right? So do you have a guess? How many neutrinos do you think we've seen?
I don't know, 30?
Yeah, I was going to say something like that, 20 or 30.
No, actually, we've seen over 500,000 neutrinos.
Oh, okay. I knew it'd be high or low. We got the wrong one.
Yeah, exactly. And it's one of the, see, because the issue is those are almost entirely produced in the Earth's atmosphere.
Right.
Okay.
Right. And so those are, but those are, we do lots of good science in that. As I said, the original motivation was to look for these very high energy neutrinos.
Yeah.
And it was just in 2013 that we figured out a way to sort through all those neutrinos and find the very high energy ones. And those we detect, you know, somewhere, you know, on the order of 2 to 3 a month of the very high energy ones. Okay. So in some ways your answer was right,
okay.
in terms of astrophysical neutrinos. Yeah. But people are always surprised, you know, by the number of actually measure, and then see about 2,700 events a second. So the cosmic rays sphere produce these muons that can actually make it into the ice.
Okay.
And so overwhelmingly, 1,000,000 to 1 from a cosmic ray in the southern hemisphere.
Wow.
Okay, so it's not just neutrinos that.
So we see 100 billion events a year.
Okay.
100,000 of those are neutrinos.
Yeah.
And about somewhere between 10 and 100 are astrophysical neutrinos.
Okay.
Okay. That's still quite a few then. Great. Okay. Let's see what else we've got then. This is quite a good one, relating back to the aliens sending the messages as neutrinos. So is it possible, from Chris Fromeyer, is it possible to encode information in a neutrino beam? If so, would it be easy to fire them through the Earth so that this path was quicker than, say, fiber optics to travel around the circumference of the Earth? So could you send information faster straight through the Earth?
So the first question is, the higher the energy of the neutrino, the easier they are to detect, right? And so, as I say, we can, we can measure neutrinos that are produced from accelerators, right? And so one could, in principle, do, something like a telegraph with dots and dashes, right? Yeah. The issue, and people talk about, could that be a way to encrypt messages, right? But the issue is it takes so much energy, right? Do is monitor like the going into an accelerator, and you could figure out the message much easier than trying to measure the neutrinos, right?
Interesting. Yeah.
And so in terms of a message coming from, we haven't seen other than from the sun and then from supernovas, right? 1987 right? They detected neutrinos from that supernova, right?
Oh yeah.
But even those, as I say, they didn't necessarily point back because they were low energy, right?
Yeah.
But we saw events that we could associate time-wise.
Okay, so they haven't
with that,
yeah.
Right? It's with what we can do now and any realistic technologies that I'm aware of, not any advantages, unless you're a neutrino scientist. Then you say, yes, we should study that very closely.
Okay. In terms of the alien messages received this week, perhaps they would have used neutrinos just because they're so good at penetrating through things in between.
Yeah, exactly. Yeah.
Okay, great. So I think we've got one more
question.
Yeah.
I think. Yeah.
So this is from Chris Boone. What is the limiting factor in localizing the origin of neutrinos detected at IceCube? Would a larger number of photomultipliers, so that's the light detectors, or increased density improve the localization?
Yeah. So I think the question was, what's the limiting factor in terms of determining where they're coming from?
Yeah, exactly.
So the first, there is a physical limitation just from the particle physics. So what you have to imagine is this incredibly high energy neutrino coming in, and then it interacts. So to a first approximation, think of it as like a BB hitting, a bowling ball, right? And fragments come out. It turns out that even at high energies, there's a correlation. There's a spread, one might say, of about a degree in the direction that the muon would come out, and that the traveling. So in some ways, getting better than a degree resolution doesn't necessarily tell you better where the neutrino was traveling. Right? There is, from theory, that there's an angular spread of about a degree from that.
Is that like a thing?
What more photomultipliers do is allow you to measure lower energy neutrinos.
Okay.
Right. So the amount of light, like the volume of light that's produced, is directly proportional to what the neutrino energy was. And so the IceCube detector is like incredibly sparse, right?
Okay,
yeah. We show it in graphics and it looks like the detectors are close together, but vertically, the distance from one sensor to another is 17 meters, right?
Okay.
Horizontally,
yeah.
Most detectors are 125 meters. There's some apart. There are some that in an inner area that's more densely instrumented, but even those are 7 meters apart vertically and about 65 meters apart horizontally. So what that does is sets what we call the energy threshold. To describe it, it's like a fishing net, right? if you have a very open net, the little fish swim through
Okay.
and catch those, right?
Yeah,
And
yeah.
so our detector is meant for very high energy neutrinos.
Oh, right. Okay.
Okay.
And
Yeah.
we're in the process now of proposing 2 extensions, one of which would make it much more densely instrumented to look for lower energy neutrinos, right? In which case, then we could get better angular resolution and see mostly those would be from the ones created in the atmosphere. And then to make it much, much bigger, instead of 125 meters apart, we can, in principle, put the sensors 250 meters apart, right? And then we would see more of the very high energy neutrinos that are more and more rare. Okay. And so right now, for the neutrinos that we detect, we're doing pretty good. But as I say, what we would like to be able to do is studies, they're called. We would like to be able to see lower energy neutrinos.
Yeah.
And that's where more photomultipliers would help more closer together. And then to find more of the very high energy ones to try localized sources, right? Then we would need a bigger instrument. And that would involve, since those are very high energy events, they produce a big volume of light, so you don't have to sample it as much.
Right.
Further apart.
Yeah.
Right. So you can basically make the detector 6 or 7 times bigger for about the same cost as the original detector because you put the sensor so much further apart.
Okay, and I guess it's relatively easy to expand it because you just drill more holes and put more detectors down, I guess, because the ice is already there, which is kind of your detector as such, right?
Yeah. Right. So I guess just to finish up, what would you think would be the future of neutrino astronomy or detection? Like what is the path in the mid future?
Yeah. So to me, the really exciting thing is getting back to your question about how did I become a scientist? Let me just talk a little bit about the motivation and then answer your question.
Yeah. Okay.
So to me, the really neat thing, and even scientists really few get a chance to experience, is opportunity to participate in opening up a new area.
Yeah.
So, more than 50 years ago, it was proposed that you could do neutrino astronomy, right? But right from the beginning, they knew it would take a cubic kilometer detector. And almost from the beginning, people started to work on it, right? And you can all provide examples, of how long it takes to go from an idea to, to a working field. So X-rays, for example, right now, lights and projects that are able to do that. But at one point, that was a question: could you come up with a detector to measure?
Yeah, absolutely.
And do
in the same way the early ones were.
Great. The neat thing about the IceCube is, it has this wide range of science. So there's still this mystery: where are these extremely high energy particles coming from, and how do they get these incredible energies? AGNs are a likely candidate. For a while, in terms of like energy balance, it looked like gamma ray burst would be good candidates, but we're not seeing neutrinos associated with the gamma rays burst so far. So that's getting to be problematic. Not, as we say in science, there's tension, not coming out. But and so the next big step, which we hope we're getting close to, is to identify, a particular location where high energy neutrinos are being produced. And probably the most likely way that will happen is in conjunction with another experiment, right? So another type of telescope says something happened, like a gamma ray burst, or some other, a blazer or something like that, and then at the time it had a peak in activity, we saw a neutrino from that direction.
Right.
Right. To count on seeing multiple neutrinos from one direction, right? And right now we see one neutrino from here, one neutrino from there, one high energy neutrino from over here. And so then we can't, each one is unique. It's like trying to learn about a family, but you're seeing individuals from many different, countries, right?
Yes.
So you learn about people in general, but you don't learn about that family, right?
Mm-hmm.
So I think that would be the next exciting thing. And then, the neutrinos themselves hold a lot of information about particle physics, contribute to that with these oscillation studies. So I think those are the kind of the three areas that I would point to and say, that's where we'll likely make the next splash.
Mm-hmm.
Yeah, that's right.
Okay. We do actually have one more question.
Yeah, quick question.
Yeah, just one.
If you can indulge us.
I think hopefully it'll be a quick one. So it's from James Gillespie again of Team Internet Explorer. So the question was, how can you actually tell the difference between the neutrinos produced in the Earth's atmosphere and the ones that are produced from beyond the Earth's atmosphere, from space, e.g. from supernovae?
Yep. So the way we can tell whether it's what we call an astrophysical versus an atmospheric neutrino right now is by the energy. So what happens is while there's very high energy cosmic rays hitting the Earth's atmosphere, they produce, but if that pion collides with something else before it has a chance to decay, it doesn't produce a neutrino. Okay, and the higher the energy the pion has, the more likely it is. And so above a certain energy, the pions don't get a chance to decay and produce a neutrino. So that means that there's an upper limit to the energy of the neutrino that can be produced in the atmosphere.
Right.
So right now, the way we definitively can tell is we look for very high energy neutrinos.
Okay.
As I described, is if we saw neutrinos in conjunction with another very high energy event.
Okay.
Gravity wave detection from a massive black hole, or from a gamma ray burst, or from an AGN, right, or a blazar or something like that. Then again, that would be a definitive signature, because one can calculate what is the probability of a chance, coincident happening in the atmosphere. And so we know, because we've been measuring these for more than 5 years with the full detector, we have very good statistics and can say, here's the chance probability that we'll see something, that would just happen to be at the same time from the same direction, right? Yeah. And so it turns out that's highly, highly unlikely, even with seeing 100,000 events, which sounds like a lot, but they're spread out, right?
Yeah.
Over. And so it's basically right now those aspects, right? Is what's the energy, and then is there some other situation? So the way we detect supernovas, by the way, we can detect them is there are so many neutrinos that come through that they would create a very small volume of light in the detector.
Yeah. So
multiple light sensors wouldn't see that, but it would all of a sudden look like the detector just got very noisy, right?
Okay.
And so instead of seeing it randomly 300 pulses a second, the detectors might go to 600 or 1,000 pulses a second.
Right.
And then it would drop back down.
Yeah.
So tell which direction they came from, but we would be able to estimate how many there were, right? And then how long that lasted, and that would give us information about the supernova.
Okay.
So that's another reason for putting sensors in closer together is obviously we have the ice instrumented, the further out we could see for supernovas.
Right,
Okay,
that's fantastic.
yeah. Interesting. Okay, I guess we'll wrap it up there then. Thank you very much. It's been great, very interesting, and great to meet you. And hopefully our viewers also found it interesting. I'm sure they did. So thanks for doing this.
Yeah, for everybody at the SETI challenge, we will open the forums in just a few minutes, and you can just keep pouring in all your science and media posts.
Yeah.
Okay, so that's it for us from SETI Control Room. This is Dr. Jim Madsen, Sam Connolly, and Juan Hernandez. Thank you very much.
Thanks very much.
Right.
Cheers. Bye.
Cheers.